Assalamu alaikum dear students. Let's continue from where we left in the last lecture. So far what we have done, we have talked about what we call the principal curvatures. Principal curvatures are the curvatures of, let me repeat somewhat, although I've repeated it many times, that at any point on a regular surface you will have a surface normal. So then you can actually take the plane of, okay, you understand. You take this plane and intersect this surface at a certain curve. So this curve is a normal section. And of course, you can have at each point, you will have infinitely many normal sections. And we take those particular normal sections which have the least and highest curvature as curves. So we call them principal sections, and their curvature is called principal curvatures. And so on and so forth. What we showed then was that those principal curvatures would be roots of this equation h square, okay, h square kn square minus en plus gl minus twice fm times kn plus t square is equal to 0. And you know E, F, G, L, M, N, H, T, they're all what we call the first and second order fundamental magnitudes, and we know quite a bit about them. So from this, we usually denote principal curvatures by principal curvatures means the roots of this equation. When we solve for kn, we denote them by k sub a and k sub b. And if we take this, if we have no sum of roots of a quadratic equation or the product of roots, especially Ka into Kb, this quantity is important. We denote it usually by K. So we multiply them, and because the product of the roots is the constant term divided by the leading coefficient of the quadratic equation, so this is called Gaussian curvature. This is called Gaussian curvature, or in general the curvature of a surface at a point. Actually, we are going to show that we can actually evaluate it without any reference to the equation of the surface. We just need the metric. We just need EFG and its partial derivatives to find K. And remember that T square is basically ln minus m square, and h square is Eg minus f square. So you can also write it in this form. Then I also talked about what we call, now at each point we have got these, um, uh, principal sections, and think about them. This is a principal section, and then there is another principal section. What's important, these principal sections are, as we showed last time, are always orthogonal. The point is, if I go parallel to these, I have a curve which has got the same tangent in the same direction as my principal section. So then these lines are called lines of curvature. So we did, I think, last time the definition. Now we do a characterization of lines of curvature. Let me write down that as a theorem. Our theorem would be a curve on a surface is a line of curvature. A curve on a surface. This is actually, you can treat this as another definition because this is if and only if condition. A curve on a surface is a line of curvature if and only if is a line of curvature if and only if the normals at consecutive points on it, the normals on consecutive points on it intersect. This is the theorem, and of course we prove it now. So we say that Okay, proof. Now remember this. Consecutive means, infinitely close points. Now you have to remember that. So a curve would be a line of curvature if I draw normals at two consecutive points. Consecutive means very, very infinitely similar close. You draw the surface normal. Of course, this curve lies on a surface. If it is a line of curvature, then these normals at consecutive points must intersect somewhere. Okay. And remember that the most trivial case would be a plane. The normal at any point on, take any curve. So if you take any curve, then the normals will not intersect, because in that case, no, that's a trivial case when curvature is zero. So we're not talking about plane here, no, essentially. Or we can say they intersect at infinity, right? But that's a trivial case. But if we have other surfaces, then of course, suppose you take a sphere, any circle, any great circle would be a line of curvature. Great circle means which has the same radius as that of, because if you take any two even howsoever close, you know normals at a point, normals to the surface, remember this, and they will intersect. So let's do the proof. It's again very easy. It comes from the definition. So just to pronounce the thing, because consecutive points, you must remember, are infinitely close when we say consecutive points on the surface. So, but we draw them a little, we will draw them, of course, a little further. Now suppose this is a line of curvature, and then I have P is a point here and Q is a point here. Oh, I didn't draw it properly, but think of it, this is a curve. And okay, now, and then there are normals, no? Think of this as a normal to here, and this is a normal to this point. Think of this is a curve on a surface, right? And they will of course intersect. If I extend these lines, they will intersect. And let's call this, this small arc from P to Q, or this vector, we call this dr. Dr means this vector, right? And then let's call this vector n, means normal at point P, and normal at point Q. Let's denote it by n plus a little increment, n plus dn. Okay. So let's now prove. Now having this, we're going to use this diagram. So we write down first our what we have constructed. Let n and n plus dn be the unit normals. Be the unit normals. Unit normals at two consecutive points. At two consecutive points. Consecutive. Two consecutive points, which we have denoted by, of course, P, which has some position vector. Let's call it R, because we are living inside the R3 space. It would have some position vector, and of course let the position vector of Q, the consecutive point, not surprisingly, be R plus small increment on R, right, as we have done before, right? And let the corresponding increment change. Let the corresponding let the direction of Q be given by, let the direction of Q be given by, okay, let me not write it with a vector, because this is a point, this is not a vector. Okay, let the direction of the Q be given by some change in increment, of course. Now I hope you understand what I'm trying to say. Now I have got what I call my parameter space. There's U going here and V go, not necessarily, think of it, this is my domain, some patch of it, and then I have a surface. I have mapped these this domain into some points here. Now I have a point P and a point Q on the surface. So there would be some change in the increments. When I say let the direction of Q be given by this pair du dv, I am saying let the corresponding change in parameters here. Of course, when I go from point P to point Q, there must have been some change in my domain, so that I got from one point of the surface to another point. So in that case, that's what I mean when I say Q की direction du dv. Now first we do the necessary part. Now if the normals and P and Q intersect, if the normals at P and Q intersect, I'm giving one look at this picture. If they intersect, what would happen is that if these two lines intersect, then these vectors n plus n, this dr vector and n vector, they will lie in the same plane. They must be coplanar, because obviously enough, if two vectors intersect, they lie inside a plane. So if that is the case, they must intersect. Then they must be coplanar. Then vectors n, or let me write n plus dn and dr must be coplanar. And if three vectors, as you have done in your 12th class, I think, if vectors are coplanar, then their cross scalar product, the scalar product of these three vectors must be 0. So which implies that if they are coplanar, it implies that their triple scalar product n plus dn, comma dr, this thing must be equal to 0. And remember, this is basically a determinant. This is a three-determinant. It's like a, b, c. I can suppose n के components ये है, right? Then n plus dn के होंगे, say a plus a dash, b plus b dash, c plus c dash. This is a determinant. A triple scalar product is a determinant of the entries. I think we discussed it last time. I think before that even. So it would be here, and of course C here. Then there would be dr. Let's call it A, B, C, D, E, F, G. So it means this is 0. Now I'm just giving them the components. n के components ये हैं, dn के हैं a dash, b dash, c dash, and of course मैंने माना है उनका. अच्छा चलो मैं डिलीट कर देता हूँ, क्योंकि तुम बड़े हो सुस्त, कुछ लिख दोगे वहाँ पे भी. Okay, anyway, फिर से खराब हो गया. Now you know that you can write this determinant as a sum of two. यानी इसको हम ऐसे लिख सकते हैं a b c, a b c. Can check, or you must have done it in your earlier class. I think you must have done it. E f g plus let me write b c a prime b prime c prime e f g. This thing is equal to 0, because you can write this as this. So the corresponding scalar products would be in terms of scalar products. I could have written it directly as is given in the notes, but for your sake I write it like this. इसका मतलब ये है plus n, of course dn dr is equal to 0. Okay, now again this is a determinant, it's like this. And any determinant around determinant wali shakal, but okay, now look at this. It has got two. If a determinant has two same rows, it repeats a row, then the value of this is 0. It means this is right. So this thing is 0. Therefore I must have. It should imply this thing, that triple scalar product of n dn
First semester we know it's a differential of a function of
variables at least. I think we did it also there, but then it was x and y. Here we have variables are u and v. N sub u du plus n sub v dv, and similarly dr is equal to r sub u du plus r sub v dv. Okay, now you substitute them. Equation 1, what do you get? You will get a triple scalar product. थोड़ा लंबा थोड़ा. So you would have, okay, you would have n की जगह आएगा n sub u du plus n sub v dv, and then I have नहीं, n तो पहले था ना, ये गलत हो गया. ओके, चलो n मैं अब यहाँ लिखता हूँ n, then I have r sub u du plus r sub v dv is equal to. Now we do the, ये डिटर्मिनेंट है, इसको जैसे ऊपर हमने ब्रेक किया था इनटू मेनी मेनी डिटर्मिनेंट्स, तो यहाँ पर भी कितने डिटर्मिनेंट्स बनेंगे. पहले हम इसको ब्रेक करेंगे तो 2, फिर उनको ब्रेक करेंगे तो हो जाएंगे, I should get 4 determinants, है ना, from this. You do it yourself. थोड़ा सा तुम भी कर लो कुछ काम, कि तुम काम तो करते नहीं हो कुछ. ओके, सो यू कैन, ये बन जाएगा हमारा डिटर्मिनेंट. और हमें पता है डिटर्मिनेंट ये स्केलर्स हैं, ये वेक्टर्स हैं, तो जो अगर डिटर्मिनेंट में कोई स्केलर किसी रो में होगा तो वो बाहर आ जाता है. तो आई एम यूजिंग दैट प्रॉपर्टी हियर, राइट. सो आई वुड राइट इट एज n, मतलब एक्सपैंड करने के बाद आई वुड गेट n sub u r sub u into du स्क्वायर, मैंने वो नंबर्स बाहर निकाले डिटर्मिनेंट से, इनटू, और बाकी शायद ज़ीरो होंगे, मुझे लगता है 4 से ज़्यादा निकलेंगे, लेकिन कुछ इसमें ज़ीरो भी हो जाएंगे. नेवरदलेस थोड़ा सा काम तुम भी कर लेना. n sub v r sub u, this is a bracket here, plus n and u are v, and u are v triple scalar product whole multiplied by du dv plus n sub v r sub v, this is, oh sorry, मैं कुछ भूल गई, d square. This thing is equal to 0. Let's call this equation second. ओके, अब हमने एक दफ़ा मैंने कहा था इसको हम आगे यूज़ करेंगे, वो कॉरोलरीज में आफ्टर वाइनगार्ड इक्वेशन के बाद हमने ये इवेलुएट किए थे, ये ट्रिपल स्केलर प्रोडक्ट, यानी